Hey class, so I got an email from a few different students actually this last night asking about problem 57 on the homework. This is a fun one and a tricky one, so I thought I'd go ahead and make a video. So what we're told here is we have a couple different disks. Alright, there's two disks, one that is a larger one, so maybe I'll draw it here. A larger disk that has a mass of 3m and a radius of 3r. That is able to spin around an axis at its center here. Okay, and then there's a smaller disk that we're told of mass m and radius r that is also at the same center, lying exactly on top of it, concentric as we're told. Alright, and they're rotating together with an initial angular speed of 26.3 radians per second. And then some disturbance occurs, causing the small disk to slide outward on the larger disk. So now we have a new situation where we have our larger disk still, but now our small disk is here. It says it's slid until the outer edge has been caught. Okay, so now in this case, I guess if we want, we could come over here and label this as 3r, as we know. This radius here is just r. Alright, now we have a situation where we have, again, we still have this radius that's 3r. Okay, this guy still has a radius of r. And so the distance here from this center of this guy to the center of axis of rotation must be, since the total radius of the red one is 3r and the blue one is r, that distance that's left must be 2r. That becomes important as we try to use the parallel axis theorem. So, let's think about how we can go about solving this problem. So for part A, as we try to solve this guy here, we're going to be using conservation of angular momentum, which I think most of you got to that point. So you're going to need I initial times omega initial equals I final times omega final. And I think the first challenge was to determine what your I values are as you attempt to do this solving here. So let's go ahead and start with that. So initial I value is just going to be equal to I of the large disk plus I of the small disk. Since they're concentric, it's just going to be the I values for each of them about their center of mass. And so since they're disks, we know that it's going to be 1/2 m. So for the large disk, we got 3m times r squared, which for the large disk is 3r squared, plus then 1/2 m r squared for the small disk. And I apologize for my cold, but what can you do? Alright, so our I initial then, we should be able to figure out. So we got, let's see, 3r squared is 9r squared times 3 is 27. So we have 27 over 2 mr squared plus 1/2 mr squared. And so that should come out to be 28 halves, or 14 mr squared. Alright, and I'm not sure if other people have different numbers, but that's what it should come out to be in this case. So, we got I initial. Oh, excuse me. Oh, this is going well. Okay, well, we're just going to leave that little line there. Sorry about that. Sometimes if I don't hit the right button and try to scroll, I just draw with my finger. So, fun times. Alright, next we're asked to find what the I final is. So I'm going to switch colors. I final now will be still I for the large disk, plus now the I from the smaller disk. And the I from the smaller disk, we're going to have to use the parallel axis theorem. Okay, so the I for the smaller disk will require the parallel axis theorem, since, again, if we look here, it's going to be its moment of inertia about its center of mass here, and then added plus mr squared, where r is this distance 2r that it is away. Alright, so if we go to add these up, we're going to have, still we have 1/2 mr squared for the large, which is 3m times 3r quantity squared, which we already know what that comes out to be, and we still have plus 1/2 mr squared. So we already know what this all is, right? That's going to be our 14 mr squared. But now we have plus the mass of the small guy times his new distance away, 2r quantity squared. Okay, so we're going to be basically ending up adding 4 mr squared to our 14 mr squared from before, because we know this all here is 14 mr squared, this is 4 mr squared, so we should get 18 mr squared. Alright, so without even knowing m and r, they'll be able to cancel out in our equation easy enough that we saw up above. So we're going to return, or you all, not we, since I'm going to leave it to you, you all are going to return to here with your new I values and use it with the initial angular velocity given to you at the beginning to try to solve. Okay, so that's for part A. Now let's revisit what part B is asking us for. If we look back up here, part B just says, what is the ratio of the kinetic energies in the two systems? Well, that's easy enough, right? For part B, all we're really being asked to determine is what is K final, and maybe I'll use KE final over KE initial, right? Well, what is KE equal to? Well, we know that kinetic energy is 1/2 I final times omega final squared over 1/2 I initial times omega initial squared. So you should be able to just go ahead and plug and chug based on the information that you already have, and again noting things that will cancel out, like our 1/2s for starters. Alright, so I'll leave you guys there and let you go ahead and try to solve this from here. Let me know if you have any questions, and hope you guys have a box-worthy day. I look forward to seeing most of you in lab today.